The topic of this video will be the dehydration of alcohols to create alkenes. Dehydration means the removal of water, so the general reaction looks like this. We start with an alcohol. In the presence of heat and an acid catalyst, we remove a molecule of water from the alcohol to make the alkene. This process is reversible. Therefore, we need to use Le Chatelier's principle to favor the products. If we remove the product, the equilibrium will shift towards the products in order to alleviate the change that we've made in the equilibrium. In this type of reaction, we typically do that using a distillation to collect the alkene product. The mechanism of a dehydration reaction resembles the E1 mechanism. However, when our substrate is an alcohol, we have a very poor leaving group in the OH- ion. This is why this reaction requires an acid catalyst. Protonating the OH makes it a very good leaving group. Therefore, the first step of this reaction mechanism is to protonate the hydroxyl. This produces the protonated alcohol. Water is a very good leaving group, and so the next step of the mechanism is the water leaving. This produces the carbocation, which can then eliminate to produce the final alkene product. Just like with an E1 mechanism, it is the formation of the carbocation that is the rate-determining step. There are other similarities between the dehydration of alcohols and the E1 mechanism. First of all, because we form the carbocation, rearrangements are possible. Secondly, we see the rate of reactivity, because the rate-determining step is the formation of the carbocation, similar to E1 in that tertiary alcohols react faster than secondary alcohols, which react faster than primary alcohols. Finally, just like other elimination reactions, Zaitsev's rule determines the major product. If we have a choice in alkene products, we will form the more substituted product. Now let's look at an example reaction. Consider the following alcohol. If we treat this alcohol with a strong acid and heat, we will get an alkene product. Let's see if we can predict those products using the mechanism of this reaction. In the first step of the mechanism, we will protonate the hydroxyl group in order to make it a better leaving group. In this case, sulfuric acid is our strong acid, or our proton donor. Protonation of the alcohol will give us the protonated hydroxyl group and the conjugate base of sulfuric acid. Our next step will be the leaving group leaving to form the carbocation. This is the rate-determining step. The final step of the mechanism will be deprotonation of the carbocation to form the alkene, but this can happen in several different ways. We can remove a proton from the carbon to the left of the carbocation. This will form the less substituted alkene product. Zaitsev tells us that this will be a minor product of this reaction, because the less substituted alkene is less stable and therefore forms more slowly. Alternately, we can deprotonate from the carbon to the right of the carbocation. Because this will form the more substituted alkene, it will form the major product. But this can happen in two different ways. We can remove a proton while the carbocation is in this conformation, which will produce the trans major product. Or we can remove a proton from the carbocation when it is in this conformation, which will produce the cis major product. Just like with other E1 reactions, if we can form the cis isomer, we will also form the trans isomer, and vice versa. So these are the three possible products from the dehydration of that alcohol, one of which is minor and two of which are major.